So now we'll calculate how we will determine the stresses in an unsymmetric cross-section. Give the moments about, for example, in this case, I have an unsymmetric cross-section. Say I know the moments about Z and Y. How do we calculate the highest stress in this cross-section given that it's unsymmetric? So let's just go through the theory a little bit here. We will consider a beam of arbitrary cross-section, and it has axes as you shown here, as you can see here. We have the z-axis and the y-axis pointed here. So you have axis y and axis z here. So this is a beam of arbitrary cross-section, right? And that'll be subjected to a moment about the y-axis and y, and a moment of ZMZ about the z-axis. And so what we want to do is we're going to assume the same assumptions for order Bernoulli beam, where this plane section remains planar. It remains plane, but also the cross section remains perpendicular to the neutral axis that transverses C. We're also going to assume that there's a normal stress sigma XX that's acting normal out of this plane at a point dA. So at this point dA, out of the plane of the page, you have a sigma stress sigma XX. Remember, the plane of the cross section here is YZ, so X is out of the plane. And so we'll assume that the remaining stresses are zero, as we have discussed earlier. And what we're going to assume, similar to order Bernoulli beam, where we assume that the stress was linear with respect to y, and you know that from this equation here. I'll annotate here so you can see that we did cover that previously. That's what we had. So stress is linear function of y. But now we're going to say that stress is also a linear function of z. And I'm going to add a constant here to have completeness. So again, all we're saying is the stress here that's out of the page of this plane is C1 plus C2y plus C3z. And so now what I'll do is to then notice that out of the page of this plane, there's a net force of 0, no axial force applied. So that's the integral of sigma xx dA equals 0, because those are units of force. And then what we have is that I can now calculate the moment about the y-axis. And if I choose this point here, then what you notice is the height is z, right? The height is z, and sigma xx is out of the page of the plane. And so when you do that, you get a positive moment in y when you integrate this over the whole surface. Then I have the fact that this point dA, for the coordinate system that I have, the y is pointed downwards, and sigma xx is pointed out of the page. And so if I do the calculation, I get the moment has to be the negative of what I'm showing here. If you do the right-hand rule, that's what you will find, and I invite you to do it. So the equation of stress is this much. So what I'll do is plug it in here to this equation, plug it into the second equation, and plug it into the third equation. When I plug this into the first equation, I get this plus this plus this equals 0. And then I plug this equation into the second equation. So sigma xx is substituted in there. I get this plus this plus this equals my. And finally, I get, when I plug this equation into my third equation here, I get also 3 terms equals mz or minus mz. So these are the 3 equations I got. And by definition, I'm going to place the coordinates y and z at the very centroid. If I do that, then this will be 0, meaning that C1 is 0. That's the only way, because if I place this in the centroid, then this is 0 and that's 0. So therefore, you get C1 is 0. So now I know that these 2 terms cancel. Moving on to the next page, you will see here that C1 is 0 here, because the moment this centroid here, that's what centroid is, I placed it in the very origin, so that's it. This is 0 and that's 0, and you get C1. You also know that I have these integrals, integral y squared dA, integral z squared dA, and integral yz. If you look at this, this is the moment of inertia, and this right here is a moment of inertia about z, while this is a moment of inertia about y. And you can see here, I have shown that. So if I were to plug in the fact that these are the moment of inertias into this equation, here, 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 and here, I don't need this equation anymore. I used it to determine the C1 is 0. So the only thing now that you have to solve is this. You can solve for C2 and for C3. And when you do that, you get that stress is equal to the formula that you see here at the bottom. That's the stress that you get in terms of the moment of inertia of the cross section. And then you get these moments that are being applied that I showed you earlier. That's what you get for stress. Now, you can determine where the neutral axis is. We know it has to go through point C, the centroid. But what about what angle is it at? What angle is the neutral axis? So we can find that angle of the neutral axis where there's no, yeah, we can find that angle. So what we can do, we know that in the neutral axis, there's no stress. So we can set the top numerator to 0, which is what I did here. And what I did then, I basically rewrote this in this manner. So I get y over z equals this. Now, if you notice, y over z is really the tangent of phi, this phi right here. So that tells you then how the neutral axis is oriented relative to y and z axis, measured clockwise with respect to this coordinate system. And so you're able to then determine where the stresses are 0 in the cross section, but you can then also determine where the highest bending stresses occur. And the highest bending stresses will occur the point farthest away from the neutral axis. So again, that's your neutral axis. So that concludes the theory portion.